Hello, and welcome to Stars, Cells, and God, the show where we discuss new discoveries taking place at the frontiers of science that have theological and philosophical implications, as well as new discoveries that point to the reality of God's existence. My name is Hugh Ross, and today I'll be your guide along with Jeff Zweerink, my colleague here, as we explore two topics, antimatter and the geological history of the Earth that's significant for life. But before we get into these discussions, I wanted to encourage you to subscribe to our channel, our Reasons to Believe YouTube channel. Click on the bell icon so that you can be informed of our new videos. Learn more at reasons.org or by following us on social media at RTB_official. Well, Jeff, why don't you tell us what antimatter is before you get into what's so exciting about antimatter?
No, very good. And that's one of the interesting things that I found is that, Einstein published his theories of general relativity back in 1915. And at the time, antimatter wasn't even known about at the time. It was, in the 30s where the theory and then ultimately it was detected. What's interesting about that is that, when you come to antimatter, it's basically the antiparticle of everything. So an electron has a corresponding antimatter particle, which is a positron. A positron has, where an electron has a negative charge, a positron has a positive charge. And there's various quantum mechanical states, and each of those, they're almost always the negative. But there's this interesting feature about that is that the electron has a mass of 511 kiloelectron volts, and the positron also has a mass of 511. So the masses appear to be the same, identically the same. And so there's not a positive and negative mass as far as we could tell, which is interesting because that's
not really antimatter.
Well, that's the question about it, because when Dirac was developing the theoretical work behind it, where these particles showed up, where they were particles of negative energy. And so there's this interesting kind of mix that I find fascinating. It's like you're doing these calculations and, well, you've got negative energy. Well, I mean, how in the world can that be? But nonetheless, that interesting, weird mathematical result ends up being an actual physical phenomena of antiparticles. But, for all that antiparticles are the antiparticle of the particle, they're the normal particle, there's this one feature where, from a mass perspective, they're identical. There is no mass and antimass as far as we can tell.
But isn't the concept if you've got an antiparticle and a particle that come close enough together, they disintegrate into energy?
That is correct.
So the matter for both goes away.
It converts into energy, yes. But that's this, again, this kind of interesting question. Why is it, why do they have opposing charges? So the charge goes away, so there's no net charge that comes out of that. But there is this, as you mentioned, when matter and antimatter get together, they annihilate into energy. So there's something different about the mass compared to all the other anti of the antiparticle. And why I point that out is that happens all after Einstein developed his theory of general relativity, is that when you look at general relativity, you could have matter or antimatter could behave differently than matter just because there's positive, negative mass. But it turns out that, depending on how antimatter actually behaves or what the fundamental properties of antimatter, you could have matter and antimatter being repelling to one another. So normally, there's ways where you could just have antimass, and that doesn't appear to be the case. But one of the ways you could do that is if when you have the antimatter, you actually have a parity and time reversal to it. Then if you were to have an antimatter apple falling down to Newton, who's a matter person, or actually being pulled due to the gravity of the Earth, you could have those be repelling, or an antimatter Earth with a positive or with a normal matter apple would be repelling, but all the other normal mass would always attract, antimass would always attract. And so why this is all interesting is that you can do theoretical work that shows all this, but it's actually very difficult to measure the gravitational effects of antimatter. And this is there's been some indirect measurements of how do antiparticles behave in a gravitational field. But there was a recent discovery by the ALPHA, it's an anti-hydrogen laser physics apparatus collaboration at CERN, that was able to trap a sufficiently large number of anti-hydrogen atoms, which would be an antiproton with a positron in it. And so you got to produce the antiproton, and then you've got to seal that, or confine that somewhere, which is not so hard because antiprotons have charge on them, and so there are ways you can use electric fields or magnetic fields to do that. And then you got to get positrons, and then you got to combine them together so that they can make anti-hydrogen. But now you have this problem that once the positron combines with the antiproton, you now have no net charge, and so confining that is hard, but it turns out there are magnetic fields associated with anti-hydrogen, so you can use magnetic fields to do that. And the long and short, without getting into all the technology, because the technology is really fascinating in and of itself, because how do you these anti-hydrogen in a way that you can now measure the gravitational influence or the effect of gravity on the anti-hydrogen?
Well, I'm curious, how did they keep away the particles? I mean, I can see where they get these antiparticles, joining them so that you got the positron joined with the anti-electron, or proton. How do you keep the matter away? Because if you get matter in there, that messes up everything.
Exactly, and I know that you're working down at half a Kelvin or something like this, so it's incredibly cold temperatures. But you'd also have to be doing it effectively in a vacuum.
Right. And
so your chamber is effectively a vacuum. You can have the antiparticles in there, and what they do to measure it is they've got this vertical chamber, and I'm going to draw. I didn't look closely enough to figure out what the scale was, but it's on the order of inches to meters. And you can confine the anti-hydrogen within the chamber, or within this with magnetic fields, but then you have at top and bottom, you have reflective, call them mirrors, but effectively they're magnetic fields that when the the anti-hydrogen gets close to one or the other, it gets reflected back in. And again, the challenge you're dealing with all of this is that the magnetic fields, if you're not careful, the magnetic fields determine what's going on instead of the gravitational influence. And so what they did is they took this long chamber, had a handful, somewhere 120 type anti-hydrogen atoms in it, confined them in there, and then slowly released the mirrors on both ends such that what you would expect is that more of these anti-hydrogen would drift out the bottom, annihilate on a part of the detector that you can. So now you can figure out, okay, there's one that went out here. Some are going to go out the top just because of the kinetic energy, but on average, more of them will go out the bottom if antimatter has the same kind of mass, or the weak equivalence principle applies, so that antimatter mass is just the same as normal matter mass. And so what they were able to find is that the amount of anti-hydrogen atoms that were going out the bottom was just, compared to what was going out the top, was just what you would expect if antimatter has the same mass as normal matter.
And engages the constants of gravity the same way.
Exactly, yeah. So it really does say gravity, or the weak equivalence principle, which says that mass is mass, and effectively it doesn't depend on the structure, type, or anything, that mass is mass. And what this means, if this result stands, and it really, it's a challenging experiment, but it's a solid result. People are going to do more and more on it. What it shows is that antimatter behaves like normal matter as far as gravity is concerned.
So the bottom line, this is another piece of evidence for the equivalence principle.
It is, and it has this significance related to cosmology, because one of the things, and even within our apologetics community, I know there's at least one fellow who was working on an experiment like this, and it relates to how does Big Bang cosmology work, because we have these things called dark matter and dark energy out there, which we measure via gravitational effects. So we look out at distant supernovae and we measure the expansion rate of the universe, and it's measuring, and it seems to be accelerating and going faster. And within the standard Big Bang model, the only way to make that happen is to have some new phenomena like what we call dark energy. I'm not going to go into explaining what it is, but effectively it's this property of space that causes the bigger it gets, the more it wants to expand. Well, if antimatter and matter behave differently in gravitational fields, then there would be ways to explain the accelerating expansion of the universe in the context of without needing some other new field in there. And so it has these large cosmological implications as well. And so this is a result that shows that other way of looking at it doesn't work. And part of what I wanted to highlight in this is not that, oh, wow, this shows, I don't know that it has great import for whether pointing towards God, except that there's just a phenomenal, the level with which the laws of physics are constant and reliable and testable is phenomenal to me. But it does really point out, this is one of those things where you say, well, duh, everybody thinks that. Nobody ever tests to see, you kind of get the experiment or you do the experiments to validate what you want to hear. There's that criticism leveled against science, sometimes by Christians and even by non-science or other skeptics. What I'm finding in this is here we are testing a foundational principle of physics, and you've got a fair number of people who say, really kind of actively almost wanting it to be otherwise.
Right.
But ultimately, what's the arbiter of this is what does the data say? And I could imagine having a conversation, the next time I have a conversation with the fellow out of our apologetics community, he really did want it almost, he was hoping to find a positive result that antimatter behaves differently in gravitational fields than normal matter does. But his response isn't going to be, wow, that's just, these people wanted to find that result. He'll look at it and say, well, that doesn't quite test everything the way I thought it did, and so here's better tests. Or he'll say, yeah, it looks like it is. I thought it was B, and it will go a different way. But by and large, that's the way scientists respond, is they are actively engaged. They're invested in wanting their ideas to be right. But the vast majority of times when their experiments show that it isn't right, they adjust what they think and move on to the next thing. And so I think this is just a microcosm or an example of how well science works and how scientists approach things. There's an investment in wanting it to happen, but also a recognition that the data ultimately drives what's reasonable to believe and what isn't reasonable to believe.
Yeah, well, I'm aware of previous experiments where they were able to produce an anti-hydrogen atom. Mm-hmm. But I think what's phenomenal here is they didn't just produce one. You said they produced over 100?
Yeah, I was trying to read through and figure out exactly. I know they can, when you can get antiprotons, you get those in bundles of about 1 million, but by the time you get down to where you're producing the atoms themselves, it's somewhere more than 10 and less than 1,000 that they get. But it's a significant amount.
Yeah, that's a phenomenal achievement.
It really is, yeah. I mean, when you think about what happens with that, it's like you've got this thing that the moment it touches any sort of normal matter, it's going to annihilate. And you've got a cavity where you can accumulate tens or more of these at a time. It's pretty cool.
It's very cool, but you actually need to have more than 10.
Right, exactly.
And I presume it's probably closer to 100 in order for them to get the kind of result that they did. Because now that you've got 100 of these, anti-hydrogen atoms, you can actually do this research to say, okay, statistically, are we getting the result that we would expect if indeed gravity in physics operates the same way in matter as it does in antimatter.
Exactly.
And, from a biblical perspective, you've written articles on this, how it was the Bible that said that the laws of physics don't change. Mm-hmm. And, scientists have been testing that. And I think this is a good example. Look, we've been testing it fairly exhaustively for decades. Mm-hmm. But physicists are committed to keep subjecting it to even more stringent tests. Because who knows, maybe we'll find at a very low level a fifth law of physics operating, which wouldn't be a threat to what the Bible is saying. But it seems like all these experiments we're doing really are establishing the biblical principle. And, the way physicists...
and the biblical principle is that the universe behaves reliably, predictably, and orderly.
Right.
There's always the possibility, there's this repeated example where we thought the laws of physics were this, and we found it's different, either in subtle or dramatic ways at times. So even if we found that antihydrogen floated up in a gravitational field instead of down, that would still be the laws of physics being constant. But it would just be, hey, we didn't understand things as well as we thought we did. So,
True. Yeah. But and the equivalence principle is usually how physicists express this.
Right.
How we can rely on physics operating in an unchanging way in space and time throughout the whole of the universe. So this is another way of affirming that principle. Mm-hmm. And this complements. I actually have an article coming out on the 29th of January where I try to do a comprehensive literature search on what is the best test on the equivalence principle and the constancy of the laws of physics. Mm-hmm. And what I discovered is they're actually probing areas of physics that had never been probed before.
Oh, yeah?
It's not just the fine structure constant and the ratio of the electron to proton mass and the force of gravity. Mm-hmm. They're actually extending it beyond that, and also adding decimal places.
Yeah.
We were saying, hey, we got it proven to 12 places of decimal. Now they're pushing it to 14, 15. But I think it demonstrates what you're saying, is that physicists and scientists in general always committed, okay, we've tested this. Let's see if we can test it to even a greater degree.
Well, and beyond that, it stands out to me how much, not only do we find that when we look at it in the lab, but how much we use that idea that the laws of physics are constant. I mean, the only example I can think of just right off the top of my head is that, for a long time, the way we produced light was to consume something. You combust something. You burn a fire, if you will. Then you're consuming your fuel and it's going away. But now, at some point in time, you realize, hey, when you heat things up, they get warm. And so now we can make light bulbs where we take filaments that can withstand high temperatures and they give off a lot of light, consumes a lot of energy. But the lights that I think are arguably the most dominant kind of light we use today are these little LED lights, which are a weird phenomena that goes on inside semiconductors where, I mean, when you look at how that actually works, which way the current flows makes a big difference. There's all these weird aspects of it, but these things work so reliably that we can make stuff that just works day in and day out in our daily life. And it's taking advantage of these obscure aspects of the way the universe works. In some sense, you burn something, that's just kind of ubiquitous. It happens everywhere you see. That's a common thing. To use a band gap where if you apply a voltage in a certain direction, you get a very specific wavelength of light, that's kind of a weird thing in some sense. And it's not a common thing that we run across every day. But even to your point about where people are testing this is that they're testing it and using it in LIGO and other things, these very bizarre, weird aspects of the way physics works, but yet it allows them to get a result that they couldn't get otherwise. And all of it says it only works because the universe behaves so stinking reliably all the time.
Yeah, we can count on it.
Exactly, yeah.
And that, again, is a biblical principle. We can count on what God reveals in the Bible. We can count on what God reveals in the record of nature.
Exactly.
So that's great.
Yeah, so I just thought that was a very interesting result. I know you've got some discussion about continents and stuff. So why don't you go ahead and...
Yeah, I'll do that. But I'm looking forward to what you're going to write on this. That'll be great. Okay, well, it's a paper that got published literally just 2.5 weeks ago in Science Advances. It came out just the day before Christmas. So, but as I read the paper, I realized this is a set of remarkable advances on the history of our planet Earth that we really hadn't been able to establish before. And it was all based on a team of 5 geophysicists who said, we can come up with a proxy for the thickness of Earth's crust. And what they discovered is that certain oxides in basalts act as a very good proxy for the thickness of the Earth if you got a wide enough sample of the oxide levels in basalts all around the world. And fortunately, basalts are very common.
So this is trying to measure the thickness of, is the goal behind this trying to measure the thickness of crust at individual locations or at any given location as opposed to using seismic data to do that?
Yeah, they're not using seismic data. And you'll be interested in this, Jeff, because this was achieved because they could use artificial intelligence.
Okay.
Because what they're doing is tapping into these enormous archive databases on rock chemistry. And so there's quite a few of these, but they're really huge. One that you may have heard of is EarthChem. Another one is GEOROC, GEOROC.
Right.
These are enormous databases where they basically archive the chemistry of rock samples all over the world.
Okay.
And so they came up with an algorithm, an artificial self-learning algorithm to analyze the databases of the chemistry of basalts all around the world. And they said this was doable because for the first time, we actually have the data we need to do this.
Okay.
You need an extremely large database to get reliable results. And then they also figured out that they had to guide the AI. And so the 5 geophysicists basically worked with the databases that the AI was analyzing and guiding the self-learning procedure to get the results. But they're able to demonstrate a very interesting set of conclusions about the thickness of Earth's crust over the history of the Earth. Not just the variations, but the actual measurement of how thick it was at different epochs.
So presumably there's got to be data today where we've got both the chemical composition and the thickness where we can measure. And so it's finding some sort of correlation between whatever the chemical composition is in current measurements and being able to, how do you get back to measuring that, say, back in the time of the dinosaurs? How would you be able to use those sorts of data? Because we don't, how do we have the rock composition there?
The first thing they did is they used these huge databases and determined that the correlation was real.
Okay.
And so now that they know that the correlation is real, they can look at basalt samples all over the world where we got good radiometric dates.
Okay, so you would need, you look at you're not looking at any sort of rock, you're looking at the basalts that are here today, finding this correlation. And then if you find a basalt that was from the era where the dinosaurs lived, then you could say, all right, now we can analyze that rock and figure out what the crust thickness was there.
Yeah, simply by measuring the oxide levels in the basalts of a known age.
Right.
You can determine the average thickness of the Earth's crust at that time.
Okay.
So that's what they're doing. And getting a large enough database that you actually get a global mean average of the thickness of Earth's crust. So that's what they did. And they came up with a number of conclusions that are quite interesting. The first one was that they were able to determine that supercontinents begin to, they build up when the crust thickens.
Okay.
So as the crust gets thicker and thicker, you have the continents coming together to form a single supercontinent. And when the crust gets thinner, the supercontinent breaks up. And they were able to demonstrate this over 5 supercontinent cycles. It's one thing to do it on one cycle, but when they saw it on all 5 cycles, they said, okay, this is a secure conclusion that when the crust gets thicker, the continents come together. When the crust gets thinner, they break up.
Did they give any mechanism? Because it makes sense to me that the crust gets thicker over time. It's not clear to me how the crust can get thinner over time because I guess I just can't see a mechanism. Did they happen to mention a mechanism for that?
Well, they said they had a hunch that this is the way it would work. The data proved that their hunch was correct. And their hunch was based on the fact that, heat flow from the interior of the Earth through the mantle, the asthenosphere, and the crust. If that heat flow varies, that should have an effect on what it does to the crust.
Okay.
So, like if you got a lot of plumes coming up from the core mantle boundary, those hot plumes will work to begin to thin the crust out.
Okay.
So they had that hunch.
All right.
But now they got the data to prove that their hunch was correct.
All right.
And moreover, they're able to show that the correlation was very good, that you really can see the continents coming together, the crust thickens. And they're able to determine the thickening effect. Like the thickest Earth's crust ever got, global mean average, is about 140 kilometers.
As compared to what today?
Well, today it's around 71, 72.
That's almost twice as thick then.
Yeah,
Okay.
and the thinnest it gets is about 50.
Okay.
So between 50 and 140. So it's a significant change in the thickness of Earth's crust.
I guess that makes sense. If thinning crust tends to spread the continents out, we've got pretty spread out continents at this point in time.
We got pretty spread out continents.
That at least correlates with that.
So, yeah, it all fits like that. And they were able to show that there were indeed 5 distinct supercontinent cycles.
Okay.
Because you probably remember in the literature, we talk about Pangea and Rodinia. And then there's debate, do we have 3, 4, or 5 or 6 of these supercontinents? And they said, we can definitively say there are 5. The first one being Kenorland, and then Nuna, then Rodinia, then Gondwana, and the last one being Pangea.
All right.
And what I saw very interesting in their paper is that they're able to show that these supercontinents, their duration gets shorter and shorter as the supercontinent cycle proceeds. And so...
Is that related to the thickness of the crust?
Yes, but it's also showing that the way the crust thickens and thins, it's speeding up. Now, what's interesting is that they saw no change in the periodicity of the cycle.
Okay.
The cycle is about 600 million years. So every 600 million years, we get a supercontinent that forms and breaks up.
Okay.
And, that pretty well fits what we know about Pangea and Gondwana. But they were able to extend it all the way back to 3 billion years ago.
Okay.
But what I found fascinating, they were able to show that Kenorland, the supercontinent lasted 500 million years.
Out of the 600 million year cycle?
Yes.
Okay. 500
million years. And the most recent one, Pangea only hung around for 120 million years.
Okay.
And you can see that with each supercontinent cycle, the supercontinent lasts for a shorter and shorter period of time. So, and at the end of their paper, they said this has significance for advanced life. It's going to be really challenging to have advanced life if the supercontinent hangs around for 500 million years, but if it only hangs around for 120 million years, that's good for advanced life. That's another reason why advanced life shows up late in the history of the Earth.
All right.
So, and they also showed that the stagnant lid theory for the Earth, it's basically gone.
Okay.
Because, there's been a long debate for 60 years now. Did the early Earth have a stagnant lid? And maybe I should define that.
Yeah, that'd be a good idea.
What we mean by stagnant lid is we have a solid crust, but it's stagnant in the sense that the plates that make up that crust can't move relative to one another. There's no subduction. There's no slipping. You get no earthquakes.
Right.
We had an earthquake a few days ago, so there'd be none of those. But with a stagnant lid, you don't have a mechanism for recycling the nutrients that life needs.
Right.
You could have life on a planet with a stagnant lid, but it can't stay around very long. The plate tectonics plays a crucial role in recycling the nutrients.
That's interesting because I think a few weeks ago we did a Star Cells and God where I was talking about the tectonic history of Mars. And Mars, a fair bit of Mars history is a stagnant lid.
Right.
Stagnant lid. So the fact that Earth doesn't is one of those things that makes us distinct.
Well, there's a little bit of it in the paper, but there are other papers that make the point that stagnant lids is the norm. The exception is where you got plate tectonics. And I thought another remarkable finding in this paper is they showed that plate tectonics has been active on planet Earth for the past 3.8 billion years.
Okay.
And what's interesting about that, the moment Earth has stable, solid rocks, you got plate tectonics.
Yeah.
So it basically tells us plate tectonics has been here as long as we've had a crust. So once you got a solid crust, you got plate tectonics. So that's remarkable, the fact that our planet has always had plate tectonics, where plate tectonics is even possible. 3.8 billion years.
Not only that, I think it's remarkable. It's kind of what I find so remarkable about the water being present on Earth is that, to my best understanding, the temperature of the Earth, average global temperature of the Earth, has been roughly within a 20C window, in spite of huge changes over the history of the Earth. I mean, you've got, glacial snowball Earths, you've got the sun's luminosity increasing, you've got huge volcanic events, you've got all sorts of things happening, and yet the stability of Earth's temperature is remarkable. It sounds like there's a similar phenomena where, though the type of tectonic activity is changed and varied, it's been stable and regular, or that it's going on has been a feature of Earth.
Right, and they do point out that the plate tectonic activity was less active in the past than it is today, but it's always been there.
Right.
And that's important for life. We've had life for 3.8 billion years, but in order to have life sustain for 3.8 billion years, you need the plate tectonics also to be there for 3.8 billion years. It's something I put in Design to the Core. I'm very appreciative of the fact this paper now establishes, yes, we have the data to demonstrate that this is correct.
Right.
And you mentioned the point about the water. You need water in order to have plate tectonics.
Yeah, they do kind of go hand in hand, yeah.
Yeah, without the liquid water, you're not going to get the plates subducting underneath one another.
Right.
So we need that. And what's also interesting is that life plays a role because the early microbes on planet Earth were playing a role in the precipitation of uranium minerals. And uranium is radioactive. And what's interesting is these microbes are predominantly doing that at the ocean boundaries between plates, so that extra energy actually played a role in producing the talc, and talc is a lubricant, which actually allows the plates to slide under one another. And so the interesting
God's
thing
putting some baby powder on the
it puts a little bit of baby powder, but the baby powder is produced there by the microbes, which makes an interesting situation for the early Earth. You need the plate tectonics for life to be sustained, but for the plate tectonics to be effective, you need the life to be there.
Yeah.
And isn't it interesting that plate tectonics kicks in at 3.8 billion years ago, and that's when we have the origin of life, 3.8 billion years ago.
That's been one thing that has stood out to me as I've just studied more over the last 20-ish years that I've been here at Reasons to Believe, is how much it's not that life is just responding to the changes on Earth. It's that as the Earth is changing, life is driving those changes. It's not that the environment is there and life is just responding to it. It's like you've got all of these complex factors at play that ensure life's habitability, the Earth's habitability. You've got tectonic activity, you've got water cycling activity, you've got solar activity, you've got life activity, and all of them play a critical role in that. It's not like one's driving and the other are following. They all have this intricate relationship with one another that keeps Earth habitable.
Well,
I just found that impressive.
You mentioned that earlier, Jeff, how there's, in the Earth's history, there's these dramatic geophysical changes going on, dramatic changes taking place in the sun. But life has a way of perfectly compensating for all those changes so that everything stays stable and we got an optimal temperature. It looks like somebody is tinkering with
it does kind of look that way, doesn't it, Hugh?
Tinkered from the very beginning, 3.8 billion years ago.
Right.
They actually closed their paper by making a brief statement, but a very significant statement, that the enhancement of the plate tectonic activity we see in the last 500 million years, 600 million years, actually was crucial for advanced life. They mentioned the Cambrian explosion in particular, that you need these dramatic geophysical events, things like the Great Unconformity, where you have massive landslides off the continents into the oceans, producing the continental shelves. Probably the most dramatic geological event in the history of the Earth. And they just make the comment, hey, this was critical to get the Cambrian explosion. So I think this paper is filled with a lot of exciting new evidence
That is pretty fascinating.
that is going to be encouraging to everybody who's a follower of Jesus Christ. And maybe we can use this to encourage people, hey, you need to seriously consider the Christian faith, because the more we learn about nature, I think that's a mantra we have at the end of this show.
Well, I have a question. I've just interacted with enough people who I would characterize, they're good scientists. I work with colleagues. There's not a lot of difference in the science we know. I mean, we know that the Earth kind of looks fine too. We know all of these things. People will know this. There are people who look at that data and say, oh, yeah, this is just all natural processes. You and I look at that and say, wow, it looks like this is evidence that God's been involved here. What do you think is the distinction, or why do some people look at this and see this as evidence against God, and why do some people look at that and see that's evidence is for God? I'm curious how you would account for that.
Well, I've run into scientists who take that approach. Hey, isn't it amazing what happens in nature?
Mm-hmm.
And it's like, what I notice is most of them are not obeying the principle of the Sabbath. And what I mean by that is not going to church every Sunday. I mean taking regular time out of your work schedule to focus on the most important issues of life.
Okay.
Hey, have you really thought about what interesting physical implications this implies? And, let's look beyond just what's happening in nature. Have you ever thought about the larger picture? Just get them to think about it. And I've noticed a lot of people who self-identify as atheists, when they begin to do that for the first time, they say, there's a lot of implications I simply haven't taken the time to look at.
Okay.
And so...
So at least some of it is just lack of, I don't want to say, it's not pejorative, lack of reflection on deeper things, I guess.
Well, you and I both know that science research is really a lot of fun. And for some individuals, it can be captivating.
Okay.
In fact, I can recall in my youth where it really captivated me to a degree. I wasn't thinking about anything else. It's almost like a drug.
Okay.
You get this high.
All right.
And I'm wondering if these scientists who self-identify as atheists are not addicted to their scientific research.
Interesting.
It's so fulfilling, so rewarding. That's all they think about. But there's more to life than just your scientific research. And so, in fact, I remember talking to one famous atheist scientist and said, have you ever thought about the fact that you're going to die someday? And he said, no, I never do. It's like, well, don't you think that's something you should think about?
Data's pretty solid on that. 1 out of 1 die. So
True. But it just shows you how powerful the addiction of scientific research can be.
I appreciate that.
But thank you
Thanks.
for bringing up that point, because that is something that I think we need to consider when we're talking, not just to scientists. I find medical researchers kind of captivated by their work. And I think that's why God said, don't just work all the time.
Gotcha.
Yeah. All right. Well, thank you for joining us today on Stars, Cells, and God. Join the discussion in the comments below. Remember to like this video and to subscribe for more content. New episodes of Stars, Cells, and God release each Wednesday and are available here on YouTube and on your favorite podcast app. Be sure to share this video with a friend, and remember, the more we know about science, the more we know about the record of nature, as both Jeff and I have described today, the more reasons we have to believe in Jesus Christ as Creator, Lord, and Savior.